We have a lot to cover this class. Okay. First thing is because we've discussed about this search method. The most important thing is the rate of convergence. And this is about the performance of your search algorithm and the like. And in order to deal with this rate of convergence, approaching speed, you have to think about one more theorem. We call it convergence theorem. Suppose that a function from R n dimension to R is continuous and differentiable on the set S. It has some special condition. This fx should be less than or equal to fx0. And that S is a closed and bounded set. That's our assumption. Suppose further that there is a sequence K. Sequence Xk is generated by the steepest descent algorithm with step length alpha k chosen by a line search. Then every point x bar that is a limit point of the sequence xk satisfies this gradient fx bar is equal to 0. It's a theorem that say if our objective function is continuous and differentiable, and our feasible set is closed and bounded, at the same time, if this S satisfies something, okay, this means this set has this kind of property, I mean the upper bound is existing, then sequence K generated by the steep descent algorithm with different step length alpha k chosen by the line search, then you will eventually have this optimality point. So let's go back to the high school. Continuous and differentiable. Okay? First thing first. How about this quadratic function? we have to choose as a closed and bounded set. So I choose from here to here. It's a closed and bounded set S. Okay? Then the function will exist in this region. And which also satisfy this. For some x, okay, all function values are less than that. Then, if you do the steepest descent algorithm, for example, let's say this is your initial point, then you will end up some point like this. Okay? Counter example. How about a function like this? Any idea? And what about if your fx0 is here? Then, in order to have the convergence, your S should be this region, according to this theorem. This theorem is very strict, restrictive one. We know that if we choose from here to there, at least we are end up here or here or here, utilizing this steepest descent algorithm, but not guaranteed analytically. But if your objective function and your feasibility reason satisfies this condition, you don't have to do the steepest descent algorithm to check if you could get to the optimality condition. It's just proven by this theorem. Okay? Okay. The detailed proof of this convergence theorem is, I think, it's on your lecture notes. So please refer to the lecture notes. We don't have enough time to cover everything. We're kind of behind the schedule. Okay. There is a couple of methods to think about this step size selection algorithm. First one is, I mentioned, bisection. Second one I'd like to talk is the amiable rule. And there are numerous other algorithms to this step size selection, such as golden section, and there are many other things, but I will only talk about these two. Okay, and thing is like this. The step size selection is nothing more than solving this problem. Suppose that f is continuous and differentiable and complex function, and we'd like to seek this one. Argument, minimize f x bar plus alpha b. Okay, that's the our lines method, where x bar is our current current position in the feasible set, And this D is current direction of moving. It could be steepest descent direction or any other direction. Anyway, this is the direction, and we'd like to find the alpha, which minimize this. Okay? If we are using steepest descent algorithm, D is right minus gradient f at x bar. If different algorithm is used, like a conjugate gradient or Newton method or something like that, then alpha will be different. Anyway, the only assumption we make is that D is a descent direction. D should be a descent direction. And you have to clearly distinguish the difference between descent direction and steepest descent direction. Okay? Descent direction, if you follow that direction, the function will decrease. And among many descent directions, there is a one, which is the steepest direction, is steepest descent direction. Okay? Okay, so let's assume that there is a theta, alpha, is also function fx bar plus alpha d. Okay? For now, x bar is fixed. We know our current position. And d, we know our current direction. And what we are thinking right now is by changing this alpha, the step size, we'd like minimize this total value. So it's just a rewriting of this thing because right now alpha is the only variable. Okay? Okay, I said this f(x) is continuous, differentiable, and convex function. Then, according to all these mathematical proofs, we can assume that this theta alpha is also convex function. And alpha is a scalar variable. If we rewrite this equation in this form, it's nothing more than just alpha bar is which is exactly the same thing. And now it is important. Applying the necessary and sufficient condition, necessary and sufficient optimality condition, to this convex function, the other way around, then the solution of this minimization is just solving this alpha bar, right? Yeah. If this is true, then this is the minimum value because we assume this is a convex function. If it's not a convex function, we are not sure. But convex function, this is true, right? Okay. And can you rewrite this in terms of this f? F is function of this x1, a vector, a multiple, x1, x2, x3, a vector, a point in a space or a point in an n-dimensional space. But, by applying this, chain rule or something, I just forgot the name of it. Jacobian. It is basically exactly the same as this is Jacobian, right? Because this is their sector alpha, their alpha. Okay? Okay. And how about this? When alpha is 0, then because alpha is 0, then is it greater than 0 or equal to 0 or less than 0? Knowing that E is descending direction. It's less than 0. So we can say that theta prime at 0 is always less than 0. Okay, and suppose we already found this alpha bar, non-negative alpha hat, which means this is greater than 0. Okay? That's our function, suppose. Any questions so far? And bottom line is, we'd like to solve this alpha. What's the alpha? Okay? The thing is like that. You have some function in this from here to some inside of some range, and you are absolutely sure at point 0 your function value is negative. Okay? And you are sure that your function is continuous. And let's assume there is you found that at some point your function is somewhere here, positive. Then there should be at least one solution between that, right? Okay? And if that's true, we can find the solution because the solution exists. Right? So that's what I'm trying to do right now. Good thing is, if the function is like that, you have only one single solution, but there is no problem, even though at least the solution exists. Okay? Okay. We'd like to find this alpha. And for every zeta alpha, zeta prime 0 is always less than 0. Since E is the descent direction. And suppose we found this one. Okay? Then now it's time to consider the bisection algorithm. Okay. That's the step 0. Initialization. Set k is equal to 0. And set alpha sub l is equal to 0. And set alpha sub u equal to alpha n. Alpha lower bound, alpha upper bound. Okay? And step k, because it's a two-step iteration, so set alpha tilde is equal to alpha sub l plus alpha sub u divided by 2. Because of this, the name bisection is king, and compute okay. And there is some if statement. If zeta prime alpha tilde is greater than 0, reset alpha upper alpha tilde and set k equal to k plus 1. Or if zeta prime alpha tilde is less than 0, then alpha lower to alpha tilde and set k increase k by 1. And if zeta prime tilde is equal to 0, then stop it. That's the bisection algorithm. Okay. Let's say this is your alpha space. This function is your zeta prime alpha. Okay? And we know that initially from 0, this is somewhere here, negative number. And let's say you found some alpha head, which is positive. And assume that right now this function is look like that for the a very simple function. The thing is like that. First, this is your lower, and this is your upper. And you take the middle, half of this space. This is your first alpha tilde. and you compute the function value here. This is less than 0. Okay? So we set this is now your lower. And this is your upper scale. And take the middle from here. And now this is your alpha. Here. And compare it. Still less than 0. So now it becomes your lower. Okay? And take the middle. And evaluate it. Now it's greater than 0. First one. Then now it's time to move your upper here. By redoing it again and again and again, you can rapidly reduce your range to locate this solution point. Okay? Okay. I said this theta is convex function, so sometimes it will not work if your function shape is very weird. But anyway, this is the kind of simplest possible line search. Any question? One thing to consider is the convergence ratio. And the other thing to consider is the tolerance. You know, in computer algorithm, it is virtually not possible. Okay? So the thing is, in real computer software, you have to think about maybe this kind of modification. You predefine a very small number of epsilon, and your function evaluation is less than that epsilon, then you can assume that this is just a solution. Okay? Question? Okay, let's discuss about this convergence ratio of this algorithm. It is true that after every iteration, the current interval alpha lower to alpha upper must contain this alpha bar. Such that theta prime alpha bar is equal to 0. And at k iteration of this bisection algorithm, and in every iteration, your range becomes just half of the previous ranges. Okay? The length of the current interval is let's say this is L, it should just half. Because we are dealing with the kth iteration, it's a 1 over 2 to the power of k alpha half. Initial length is from 0 to alpha hat, the initial length is alpha hat minus 0, which is equal to alpha hat. And another observation is a value of alpha such that alpha minus alpha bar, the norm of this is less than epsilon, is another word of this, because this alpha bar is real analytic solution and alpha is current location of this alpha. Okay? Can be found in almost log base 2 alpha hat over epsilon, and there is one funny sign. This sign is upper bound of something. Okay? We don't know exactly what this is, but this value should be less than or equal to something, the upper bound. Okay? So that's it's a number of steps. Okay, so it is heavily dependent upon the initial range, the length of initial range. At the same time, your tolerance epsilon. If your initial range is same as your tolerance epsilon, then it's a log 1, which is 0. You just have the solution, right? Okay, question? Okay. One more thing to mention is, in a computer program, this is absolutely necessary. Without it, you will have infinite number of iterations, because sometimes it's a minus 0, 0, 0, 0 something, and next time it's plus 0, 0, 0 something, and you will iterate like that because of these numerical errors. So you need to have this one, but if you have a very small epsilon, you still have the possibility to have this infinite number of iterations. So to write a robust and safe algorithm, there is another kind of stopping mechanism. You need some stopping condition, stopping criteria. One thing is number of steps. If your iteration number k exceeds like 10,000 or 100,000, then you just stop. That's another tutorial. And size of range. If you offer alpha upper minus alpha lower. But if the size of your range becomes to some amount, then you just stop. There's another one. And this is the third. You can use these three at the same time, or you can use the combination of all these stopping criteria. Question? Okay, there's a various golden methods with this section approach. If you see some line search algorithm with section word inside of this name, it is almost the same as this bisection. Golden section method is nothing more than section method visualizing golden ratio 0.33 something and something like that. Okay. Let's say there is a function and we would like to find the minimum of it. But the most brute and straightforward way to do this is take n equally spaced sampling point. Like this. And you evaluate the function at every point. And the next step is find the smallest 2, which is this. Then you can redo it, divide it by 10 or something like that. And redo it, and you will converge the solution very rapidly based on your number of equally spaced sections. But however, this is really computationally expensive. Evaluating a function takes lots of time. So that's why this is really a very nice method in terms of this convergence ratio. In a very limited number of iterations, you can quickly approach the solution. But computationally expensive, so there is lots of trade-off. The other end, there is a bisection. You just cut it half. But for this kind of golden section method, you plug in the computer. This is your initial lower, initial upper. And this is your golden ratio division. So based on this comparison, you can take this in next iteration or this in next iteration. Things like that. If there is a lot of something section algorithm, but the basic concept is exactly the same. Okay, and let's talk about this amino group. Sometimes people call amigos group or just amigo group. Okay. You know, this section method is exact line search method. Convergence is guaranteed if you satisfy the initial assumption. For example, this is your negative and this is your some value at positive, and you know this is convex function, then the solution can be guaranteed. After some number of iterations, you are absolutely sure find the solution. Exact line search. Golden section method, same. Exact line search. But this amino is one of these traditional inexact line search. If you think about exact line search versus inexact line search, of course, exact search is much better because it's exact. You're sure to get the solution. But why people tend to use inexact search? Time and efficiency. Usually, these exact line search are computationally very expensive. You have to evaluate a lot of function evaluation. To minimize those kind of evaluation of function, people invented this kind of inexact line search. It is inexact, however, efficiency-wise, it's very nice. Okay. Think of it. In this steepest descent algorithm, you have to first evaluate gradient in your point, and this gradient becomes your direction, and you have to do the line search. If you move to the next point, you have to evaluate the gradient, and you have to do the line search once again. So in steepest descent algorithm or any other kind of this descent algorithm, you have to evaluate or perform a line search algorithm in every iteration. So efficiency really matters. If we inexact line search, the concept is increase the efficiency by sacrificing the accuracy. Okay? There is nothing like increase the efficiency by increasing your accuracy. Right? Armion rule is one of the several inexact line search methods which guarantees a sufficient degree of efficiency. Not the exact solution, but guarantees a sufficient degree of efficiency. And this is it. Armion rule requires two parameters: epsilon, which is from 0 to 1, and sigma, which should be greater than 1. You need to list two new parameters, and suppose we are minimizing a function, same function like zeta alpha. It's given like right? We'd like to minimize zeta alpha. And we know that for every zeta, it is always less than 0, because we are taking descent direction. Then, now we introduce some inexact term. This zeta alpha at alpha is 0 is approximated by zeta 0 plus alpha times zeta 0. This is just a line, right? This is alpha, this is your zeta alpha, and I don't know, maybe your function is like that. And this is approximated by the straight line. And the slope is zeta 0, and the y-section is zeta 0. And alpha is the variable. Right? Straightforward. But anyway, we introduced approximation. Okay? And let's define zeta at alpha is zeta 0. It's exactly same. But there is a epsilon multiplied by your slope. And since we are only talking about the line search, we have to follow this descent direction, so we only have to consider this. Right? Okay, we introduce the zeta hat. So for illustration purpose, let's assume we have a theta alpha function like this. We only have to consider this part, alpha is greater than 0. And if we draw this one, this is something like that. It's a first order approximation function at alpha is equal to 0. This is delta 0 plus alpha and right? The first order approximation here, and what will be this theta hat? Everything is the same, but you only have this epsilon multiplied to your slope, and this epsilon is positive number, but less than 1. And maybe something like this. Question? And just saying, this Armino rule, we also like to find this alpha bar. And according to this Armino rule, we assume this is acceptable. Theta alpha bar is less than theta bar alpha bar, and theta sigma alpha bar should be greater or equal to theta hat sigma alpha bar. Okay, so let's look at this figure once again. The first condition is your theta should be less than theta hat. This is your theta hat, and this red line is your theta. So the region where this equation falls is this part. Right? So every point pitches inside of this part, but actually from 0 to here, satisfy your Armino rule. So the thing is, the slope, and you decrease the slope by 1.5 or some 1.1 or something like that, you will have enough of this range. And if you move to any point, this alpha bar or this alpha bar, this alpha bar, that will be okay for your step size. Okay? The best possible thing is you choose this, right? But because this is inexact line search, you cannot point out, but you only give this range. But there is one more problem. According to this, you will always, this is always true, if you choose a very small alpha bar around this area, the first equation usually always holds. So we have to avoid too small step size. So that's why the second thing comes in. This is only to prevent too small step size. Okay, and sigma is greater than 1. So your theta hat should be less than 1 equal to your theta. If you choose those reasons, this region this blue line region is where your theta function is greater than theta hat. Okay? But you're not supposed to take that value directly. Sigma theta bar, sigma alpha bar. This is alpha. So the thing is, if we choose, for example, sigma as 2 for simplistic purpose, then from here to here, you can reduce it to the half. So half of this is around here, and half of this is around here. Okay? So this region or this region and this region. So the cap of these two regions is around these two regions. So by applying Amiho rule, your selection of the step size range will be this region. And among this region, you can just select anything. And usually it works because we assume that continuous, differentiable, and any other nice assumptions. That's the Amiho rule. And let's write the algorithm. Anyway, because it's an inexact search, it only gives the acceptable range of step size. Okay? Step 0. Initialization. Set k is equal to 0. And alpha 0 is equal to initial guess. Set k. If the first condition is satisfied, then choose alpha k as step size. If I just assume that sigma is 2. If you do this again and again and again, then but anyway, this also includes the initial guess. like the line search method, but there is no other way to avoid this initial guess. Okay, question? Okay. Don't worry about it. This Amigo rule is part of your next homework here, so you will get accustomed to this. And you're supposed to write a MATLAB code for this Amigo rule, and you're supposed to compare the efficiency of this Amigo rule with the bisection method. Okay. Okay. Next step, I'd like to talk about this convergence analysis with this Amigo rule and convergence analysis of this steepest descent algorithm with bisection method or with this Amigo rule, but it will take lots of time. So I will just skip it, and you can refer to the lecture note and follow the steps of the proofs. Anyway, I'd like to mention one more thing. If our function is in the quadratic form, for example, quadratic form, if your function is like, this is just another example, Q. It's a generic quadratic form. You know, in high school mathematics, if you were asked to write a general form of the quadratic function, then you are supposed to write this, and the condition is this. Exactly the same thing. Some value or something like that. So let's say this is one example of typical quadratic form, and you have to give this quadratic matrix. For example, like plus 4 plus minus 2 minus 2 plus 2, and for Q plus 2 minus 2, then you are supposed to run this steepest descent algorithm with bisection or Amigo rule with your hands. Because the function is really easy, and there's no, this is not that much computationally expensive. So anyway, bottom line is, given this function, and your final exam problem could be like that. If your function is like that, find your optimal solution using paper and pencil, utilizing the steepest descent algorithm. And your stopping criterion is the iteration is maximum iteration is number 5 or something. So you are supposed to know every possible step of this. Okay? Okay. So far, we talked about the descent algorithm, steepest descent algorithm, and there is, this is not the only algorithm available to find the solution of unconstrained optimization. There is a very famous algorithm called Newton's method. Okay, let's go back to the basic. Assume there is a problem P, unconstrained optimization, which is in the form of such that right? And we know that x is equal to x bar, at this x bar, f can be approximated by function gx, which is quadratic Taylor expansion. This is quadratic Taylor extension of function f(x). X is the x bar. And I'll just use this gx to alleviate some confusion. But anyway, this gx is quadratic function. It's a quadratic Taylor extension, so it is a quadratic function. And this gx, this quadratic function, is minimized by solving this. Right? This will be minimized by this. Why? So it's a quadratic function. This is exactly the same thing as gradient fx bar plus Hessian x bar x minus x bar is equal to 0. Okay? Which is x minus x bar is equal to minus Hessian at x bar inverse and this is matrix times vector. Is a vector. So this is a vector, and we call this Newton direction. Or someone call it Newton's step. If you're confused about this one, if you apply this gradient sign to here, then you will get exactly the same this. Okay. Let's quickly discuss about this Newton's method. Step 0, initialization, and we need initial guess of the initial point given x and set k is equal to 0 initial. Step 1 is calculation of your Newton direction. dk is minus Hessian at x0, x k minus 0, k minus 1, no, k, sorry, minus Hessian xk inverse gradient f xk. If your Newton direction is just 0, then stop. Step number 2, choose step size. Step 3, set xk plus 1 is equal to xk plus alpha k dk. K is k plus 1 and goes to step 1. Okay, that's the basic point of Newton's method. At the initial guess point, you calculate the Newton's direction. Okay, if your direction is 0, since this is a vector, then you just stop it. But if you have some direction, you move along this direction with step size of exactly, say, to number 1. Then move it and go again and again and again. And the important thing is that in descent algorithm, steepest descent algorithm, we assume that this is right. The most important thing compared to the steepest descent algorithm is that the steepest descent algorithm utilizes the gradient. But in this Newton's algorithm, you utilize Hessian. This is the slope of the function. And this is the curvature of the function. 1 time derivative, 2 time derivative. Utilizing this 2 time derivative, it usually, in most cases, converges to the solution much faster than this steepest descent algorithm. However, calculation of this Hessian takes also lots of time. Okay? There is a trade-off. However, this is the basic Newton's method, but can you notice something wrong or something weird? You can apply line search method once again here, which will also increase your convergence ratio. But basically, Newton's method doesn't just assume that you need step size, but if we just improve this Newton's method by applying bisection method or Arminian rule or golden section or whatever line search algorithm here. And the bad news is in steepest descent algorithm, the next point is guaranteed to less than previous point. But this is not true in Newton's algorithm. This is not guaranteed. And also, we need some more assumption. Since we utilize the inverse of the Hessian here, which automatically include the assumption, this Hessian of the function should not be singular. If the Hessian is singular, we cannot use it. That's the Newton's method. And okay. Let's find out one thing. It's another proposition. If a Hessian matrix is positive definite, then this Newton direction B minus Hessian inverse gradient x. Gradient x is descent direction. And in order to prove it, it is just sufficient that to show this gradient x transpose E is, this is minus we just apply this gradient f in front of this Hessian. If we just show this is less than 0, then this direction B is descent direction. If B multiplied by this function gradient is less than 0, then B is the descent direction by definition. So which is we have to show this is true. Yes, right? Which means we have to show this Hessian inverse is positive definite. Okay, let's prove it. Since this Hessian is positive definite, and if there is a vector, non-zero vector, 3, then Hessian inverse 3 over transpose Hessian inverse 3 Hessian inverse B is a vector. Since B is non-zero, this is non-zero vector. Because Hessian is positive definite, so for every non-zero vector, this form, if this we can also this is x, should be greater than 0, right? That's the definition of positive definite. If we derive this one, is it will reduce this form, and this is already also greater than 0. So for every possible non-zero vector, this holds that this Hessian inverse is also positive definite. End of